So, plan is, you don't need to write any of this down. This is stuff we put in our notes before. We'll look at it again probably Monday. But so the plan is quiz on Tuesday. Now it's borderline close. It could be Monday, but I know we may have some going on tomorrow. But anyway, we'll do it Tuesday. That'll give us a chance Monday to continue to work on these things. We don't really have anything new to do. I mean, I say that there's no really new concept to introduce, but there certainly are new scenarios that you run into in these problems that you need to see and work through and work on and practice and so forth. So that's what we're going to be doing a lot of, is me kind of working through that, answering questions, and giving you some work time on that stuff. Okay, so the plan is tomorrow, class as usual, we'll go through stuff, but it'll be recorded. If you're not going to be here, tomorrow, let me know here at the end of the class today, and I'll give you, there is another handout that I'll have tomorrow of just more problems to work and just to continue practicing different types of problems. Okay, so just let me know at the end of class here. But everything will be recorded and so forth for that. So we have our parametric equation. So these were the things we will have to remember about parametric, with the x and the y being the horizontal and vertical. So the x prime and y prime were the horizontal and vertical velocities. The slope formula, which was y prime over x prime, and then the speed formula, x prime squared plus y prime squared. So everything was based off of x prime and y prime, the derivatives of those. That was parametric. We're going to do the Luke Skywalker problem today, which we're going to work on that a little bit, which is the kind of the Shanghai problem a little bit. That's related anyway to that Shanghai as far as how we set it up. So we have that. That's with parametric. And then we had our optimization. So we had our steps. We had some of those again today with finding max and min and so forth. So we'll go through that. Those are our steps. And then we got this new thing, this related rate business here. So let's, let me see. Okay, so let's start with the book problems. Let's start with those related rate problems. So like number 4, you had the shadow, right? And then you have the lamppost kind of deal. We had the person and we had that, right? So we kind of set that up a little bit yesterday. We called this S, we called that X. This would be X plus S down here, this side of this triangle. How tall was the lamppost? 12? 12. Okay. And they wanted to know what? How far? How long is the shadow when it's 10 feet from the lamppost? At what rate is the shadow lengthening? Okay. So it's a matter of just identifying those rates. So how far was he from the lamppost? What distance is that? How long is his shadow when he is 10 feet from the lamppost? So what's the 10 in this picture? The X, right? And we're wanting to find the S, right? So, and then the second question is how fast is his shadow lengthening? So what is that? S prime, right? So we need to relate X and S. Well, this is not going to be a Pythagorean theorem situation, because then you're going to introduce another variable like the hypotenuse, which isn't even talked about in the problem. So that's how you would know you don't want to do a Pythagorean theorem, because you don't want to introduce a new variable that's not even talked about in the problem generally. So this is where yesterday we talked about this similar triangle situation. Okay, we have similar triangles. So this, and how tall was he? 6 feet. Okay, and those aren't going to change, the 6 and the 12, so I can put those right in there. So we have this proportion 12 over x plus s equals 6 over s, and then we can cross multiply those, and we get 6x plus 6s. When we cross multiply there, we can subtract. Now this one happens to be so basic, it's almost difficult because it's so easy. I mean, we end up with s equals x, which is weird. And then what would be the derivative of that? Well, it'd be s prime equals x prime, right? With respect to t. Remember, everything's with respect to t. So it turns out that his shadow is lengthening at the same rate that he's walking. Not only that, but s is equal to x. So when he's 10 feet away, or when his shadow, which one was it? I can't remember. When he's 10 feet away, how long is his shadow going to be? 10 feet, right? And when he's walking, how fast is he walking? 7 feet per second. So X prime would be 7. So what's S prime? Also 7. So it just kind of coincidence. It turned out that way just because this worked out that way, right? Because it was 6 and 12. If it would have been any other height, we'd have had some other numbers in there and so forth. Okay, so nothing too weird going on with that one. Okay, so then, all right. So on 7, what was 7 about? Was 7 the rectangle one? So you got a rectangle, you got length, you got width. You can use X or Y, doesn't really matter. And then it says the width is increasing at a rate of 2 centimeters per second. So what? I'm going to write that down. What would I call that? W prime. W prime would be 2. The length is increasing at a rate of 3. It's L prime. Okay? At what rate is the area changing, increasing, when the width is 4 and the length is 5? So the width is 4 and the length is 5. But those are changing quantities. Now, W prime and L prime aren't changing. They're going to stay the same the whole time. But those are changing quantities. So I don't want to put those in right away. So I'm going to write A equals LW. I'm not going to plug the 4 and the 5 right in there right away because those are changing amounts. Only things that will not change in the problem. So this rectangle is increasing like I'm dragging down that corner. So we do the derivative. So this is very similar to one we did in class. Derivative first, leave that alone. So we got to do the product rule like that. And now we can plug in all our numbers. And this was a really nice one too because all the numbers are there. We don't even have to find any numbers at all. And so this would be the easiest type that it's ever. They pretty much just give them to you. You didn't have to find them. 12 and 10 is what, 22, and everything's positive because everything's increasing. But what would be the units? Per second. Because the 3 is centimeters per second, and the 4 is centimeters. So when we multiply those, we're going to get centimeters per second. Okay? So that's it. I mean, that's a very basic kind of a related rate problem. We said that it was identify the different amounts and rates, so that's where we wrote down the different things that were in the problem. Then we said draw and label diagram, which I did. The picture wasn't that important really here. Write an equation that relates them because they want to know how fast the area is increasing. So what relates area and length and width? Well, that's area equals length times width, so that's an easy one. A little harder on the shadow one. We had to see the similar triangles, so a little harder to write the equation on that one. Do the derivative of both sides with respect to t, so we did that. Put your values in. There it is. Okay, so now obviously we're going to get into some that are a little trickier to set up, but as the more you do them, the more often you do them, the easier they become as you see the different ones. Okay, let's go. Now let me see what order. Yeah, let's stick with related rates here right now. So you could do it on your homework paper. Go to your notes. Maybe go to your notes would be better. Let's get into this related rate business a little bit more detail. Let's do this problem right here. And I don't know if you want to write it down or not. Okay, a cone problem. We are going to, I can almost promise you on the next quiz, one of the related rate problems is going to involve a cone. They're just very, very common problems for related rate for whatever reason. There in every calc book, every calc class ever took, this is one of the problems we get. So not unusual to see it on the AP test as well. Okay, sand is poured on a beach, creating a cone. So you've seen those piles like grain elevators, the corn and stuff, right? They dump it down, it makes this great big pile. It's a cone-shaped pile. They call it a conical pile. Okay? And they tell you that in this cone, the radius is always equal to twice its height. Now that's an important thing here because it's kind of like the shadow problem. One of the reasons we spend a lot of time doing the cone problem, because something happens in the cone problem that doesn't happen in the rest of the problems, a lot of the other problems with related rates. Some of them it does. But it makes us, we do have to reduce down the number of variables, because a lot of times there's too many variables in the problem. Now, first of all, it says how fast, it talks about the sand is being poured at 20 cubic inches per second. Now, when you see cubic inches, what do you think of? Volume. So we need the volume of a cone. That's the formula we need that's going to relate the radius and the height. What is the formula for volume of a cone? Anybody know? What's a cylinder? Pi r squared times height. A cone is 1/3 pi r squared times height. If you took a cone like that was the same height as a cylinder with the same circular base, you could take 3 cones, you could fill up 3 cones and pour it into the cylinder and fill the cylinder. Right? You used to do that when I taught 8th graders. We were doing volumes. We used to fill. Did you ever do that in 8th grade? 7th grade, remember that? Used to fill a cone with water and fill the cylinder, 3 of them would exactly fill. Whatever. So it's 1/3 pi r squared h. Now you should probably memorize that formula, but I would think on the quiz I'll probably give that to you. Right? But the number of these problems we'll do between now and Tuesday, I would think you would probably know the formula. Okay? But that's the volume of a cone. Now, when we do, if we're going to do the derivative of that, we'd have to do a product rule, right? Because of the r and the h, and we'd have an r prime and an h prime. Now, that was not a problem in the rectangle what we did. We had stuff about that. But if you look at this, the only number they give us is 20 cubic inches per second. Now, what is that? No, it's not h prime. It's v prime. Right? It's v prime because it's the rate of change of volume. It's cubic inches. So that's v prime. Now, is that positive or negative? Positive, because the volume is increasing. We're pouring sand on the beach and it's creating this cone, so it's positive. It's the only number we have. And what are we trying to find? We're trying to find h prime. Right? So if I was to do a derivative on this, and then I would have r's and h's and r primes and h primes, right? I would not have near enough stuff to plug in to find h prime, right? Because I don't know r prime, I don't know, right? I mean, I don't have enough numbers. See, that last problem, we had all those numbers in the problem, so we could just have all these variables, throw in numbers, we were good. Well, the key is that first sentence. What's it say? The radius is always, and that's what happens with these cones. As these cones grow, it comes back to similar triangles. They grow, the radius and the height grow in some equal ratio. Okay? They grow in some proportion. And you'll be given that in the problem. Now, in this case, we're told r is equal to 2h. Now, I got 2 choices here. One choice is I could do the derivative of that too, right? So if r is equal to 2h, what's r prime? 2h prime, right? And so I could do that and I could substitute stuff in. Now, I typically don't want to do that because I got to do a product rule on this, and then that would cause me to have to, do that right, make sure I didn't screw that up, and then I have to do a bunch of substituting later. I think the easier thing is to just substitute right now. I think the easier thing to do is to just substitute that 2h right in there right now. You see what I mean? Just put 2h in for the r right now. So what I would get is v equals 1/3 pi. I would have 2h squared and then times h. Now, the other mistake people make is then they just do their derivative now. Well, no, then you'd still have to do a product rule. You need to simplify this. So this is going to be, this would be what, 4h squared right here? And then the 4 times 1/3, that'd be 4/3 pi h cubed. That's what I want to do. So this is a little bit like what we did with optimization problems, where we had to get things in terms of one variable, right? But I think on the cone problem, this is good, because there's an R and an H in the cone equation, but every cone is going to have some ratio with its radius and height. Every single one is going to have some ratio with the radius and the height. So it'll be given to you in the problem, or somehow it'll be given to you with the dimensions of the cone, which I'll show you on the next problem here. Okay? So you can always get that down into that, because almost every cone problem is interested in the height. You know, somehow either the height's changing at a certain rate, how fast is the volume changing, or the volume's changing at a certain rate, how fast is the height changing. So it's always one of those two situations. People on the video are like, what just happened? All right, so now we're ready to go. What's our next step? Do the derivative, right, with respect to t. So v prime equals, now remember the 4/3 pi, that's just a number, so it's just going to hang out there. So we're going to do the normal derivative, so we bring the 3 down, so that'd be 4 pi h squared h prime. Right? We got to do the normal derivative and then kick out an h prime. All right, now we're good to go, because we know that v prime is 20, and we know that h prime is what we're looking for. And then h, it says right here, how fast is the height changing when the height is 2? So that they want us to plug in a 2, and then they also want us to plug in a 6. But I mean, normally I would just ask you one of those questions, right? But just to see that you're getting 2 different answers. Okay? So we get v prime equals 4 times pi. Oh wait, v prime is 20, right? V prime is 20, so let's put our 20 in for v prime. So we get 20 equals 4 pi. We're going to put a 2 in for h, and then we're trying to find h prime. Right, so this would be 20. Now you can just do a solve on that right there, call h prime your x, or this is 2 squared is 4, that'd be 16 pi h prime. So h prime would be 20 over 16 pi. And I'm fine with that answer. Now you should put units on it. So it's 20 over 16 pi, and that would be what? 0.398 inches per, would that just be inches per second? It'd be inches per second, right? Because this is height we're talking about. Now the reason is this would be inches cubed over here. And then our h was 2, that was inches, and we squared it, so that'd be inches squared. So we'd have inches cubed divided by inches squared, so we'd have inches per second. So I don't care if you do the decimal or the 20 over 16 pi. You don't have to change it to a decimal. You can leave it 20 over 16 pi. Okay? Now, if you put a 6 in there for the height, so as it gets taller, you put a 6 in here, that'd be a bigger number here, and you would divide, you have a bigger number on the bottom, that'd make it smaller, right? So it's growing slower as it gets up there, okay? Because it's spreading out too, right? It's spreading out. So when you have a smaller amount, as that stuff drops, as the sand drops on there, it's growing, but then as it grows, it takes more and more sand to fall down and to fill around, right, as it goes out. So it's not growing as tall later on. Okay, that is a basic cone problem. Okay, now let's take a look at this next one. I'm not going to, you can draw the picture if you want. So this is another cone problem. Now notice the cone is the other way around. Whenever we have a water tank, like a cone tank, then it's facing this way, right? The tank, so the water's going in here like this. So the direction of your cone is kind of important, right? I mean, so if you got sand or something piling up on the ground, it's going to be that shape of a cone. If you've got a cone that's holding liquid, it would be this shape of a cone. But water is draining from a tank, so we got water in this tank, right? So here's our water level somewhere in here. So the key to this is this. It says The tank is 16 meters tall. So this is 16. I should use red. The tank itself is 16 and a radius of 4. But the water, right, is here. Do you see how those are similar triangles? So the radius of the water and the height of the water, well, if you look at that, what would that be? Now, the height is just this part, right? So then the 16 is that whole part. So 16 over 4 would equal h over r, right? And when you cross multiply, you'd have 4h equals 16r, and then you divide the 16, and you would get 1/4 h. Now, why did I solve for r? Well, think about the last problem. We usually want the r out of there, because look what it says. How fast is the water level falling? So it's h prime we're asking about. They rarely ask about the radius. How fast is the radius changing, right? They rarely ask about that. Okay, so the last problem was a little easier because they just said the radius is twice the height, so you knew right away that r was 2h. Here they just gave you the size of the cone and the tank, and then so you kind of have to set up your own proportion for radius and height. Okay, and I wouldn't even have had to set up the proportion. I could just tell, well, look at this. The tank is 4 times more than the radius. So that tells you right there that the height is 4 times the radius. So I could have just done, that, right? I could just look at those two numbers and I could say, oh, okay, the tank is 4 times higher than what the radius is. So the 4 times the radius is the height. So 1/4 of the height is the radius. And I always want to solve for r because then that way I can take the r out of my volume equation. That makes sense? Okay, I can take the r out of my volume equation. So now the rest of this problem is going to be very similar. So we start with 1/3 pi r squared h. Now we're going to take the r out of there. Okay, so r is 1/4 h, right? So I take the r out. So what's 1/4? That's 1/16. 1/16 times 1/3 would be 1/48 pi. I could put the pi up top. Actually, I usually don't do that. I usually do that as 1/48 pi. So 1/48 pi, and then that'd be h squared times h, that'd be h cubed, right? So every cone problem is pretty much like that. I should say every, but you're right. Almost every cone problem is going to have, this kind of scenario. So somehow we know the ratio, the connection between the radius and the height, and that allows us to take the r out of the equation, get it just h, and then we can do our derivative. So now again, they gave us this. Now that'd be negative, right? Because the water's draining out. So the volume is decreasing. So this V prime would be -2. And then they want to know what's H prime when H is 12 or H is 2. Okay, and then you would just go from there. Okay? All right, so that is the world famous cone problems when it comes to related radius. All right, so let's move on to our packet, business packet. What happened to my business packet? Did I close it? All right, so which ones of those do you want to talk about? Yes, I yelled at you. I yelled at you down the hall that you were way down. There you go. Actually, they were right here under my book. And then I printed some more. But, anyway, yeah, I sounded kind of silly. I walked out into that hall and yelled at Scott. I was looking at me. All right. So, number 19. The cost per unit to produce a type of radio is $60. The manufacturer charges $90 per unit for orders of 100 or less. To encourage large orders, they knock 10 cents off per radio for each order in excess of 100. So that means if you order 100 radios, they're going to be $90 a radio. If you order 101, they're all going to be $89.90. All of them, not just the ones over 100, but all of them, right? The price for every radio, it says $89.90 per radio. Order 102 radios is $89.80 per radio, so for all. Find the largest order the manufacturer should allow to obtain max profit. So obviously before 100, it's $90, right? So they're going to make more profit with every radio, right? Because it costs $60 to manufacture, so they're going to make $30 on every radio. So all the way up to 100, they're making $30 more, right? So they want to sell more radios. But then at some point, they start knocking the price down a little bit. So now you're making a little less on every radio, but you're selling more of them. So, right, you got those two competing factors, right? So at some point, it's going to maybe go the other way. At some point, the radios will go below 60, and then all of a sudden you're losing money, right? I mean, so that's the problem. So there are a lot of different ways to approach this, but if you're looking for one way, a lot of these problems, we're not getting into a lot of very difficult ones that have a whole bunch of different things. Most of the ones we're going to do when it gets to this business kind of thing are more linear. In other words, for every radio, we're knocking off 10 cents. That's a linear relationship, right? That's like slope, right? You know, one more radio, knock off 10 cents. One more radio, knock off 10 cents. One more radio, knock off 10 cents. It's like a rise over run thing, right? So the slope is like the 10 cents. Now, you got a couple ways to do it. Now, I don't know if some of you I know looked at the answers that I had in the business packet that I put online. But if you looked at, Sam Hari was in here this morning, and he was showing me in the packet where one of the examples, and they went through this and how they did it, kind of like an ordered pair. So there's two different ways I think you could set this up. Now the key is, and you were in here, Will, you were asking earlier, the key is you got to understand that profit is revenue minus cost. And you got to understand that revenue is what? X times P, the price. So your equations you're setting up each time are basically this, right? So the key to these problems is getting that price. Getting that. That's typically in the story problems. Now, in those earlier problems like 15 and 13, I mean, they just gave you the P equation, so you just times it by X. I mean, they just gave it all to you, so you just do it. So the key to setting up these story problems is to figuring out if X is going to be your number of units, then P's got to be the price, and you got to figure out what the price. So what is our price? Well, it's $90, or it might be $89.90 or $89.80. We're knocking off $10 every time, 10 cents every time. So you got two ways you can do it. One way would be to just think your way through it. One way would be to say, okay, it's going to be $90. My price is a little p. Little p is going to be $90 minus 10 cents for every, right? Don't you multiply in that situation? For every what? Radio over 100. How do you write the number of radios over 100? If X is the number of radios. Well, if you got 101 radios, what's the radio over 100? If you got 102 radios, what's the radios over 100? If you got 103 radios, what's the radios over 100? If you got X radios, what's the radios over 100? X minus 100, right? I mean, here it's 1. That's 101 minus 100. 102 minus 100. 103 minus 100, right, is 3. The number of radios over 100 is X minus 100. So one way is to just think your way through it. So you just say, okay, it's $90 minus 10 cents for every radio over 100.
If X is less than 100.
Right, then that doesn't work. So this equation is only good for that, right? For X greater than or equal to 100. Now, here, so that's a great question. So if X is less than 100, I don't have to worry about it though, because if X is less than 100, what's little p? It's just 90. So I can just calculate that, right? And so when I get down to my justification, it's going to be easy because less than 100, we're going to make more all the time, right? The more radios we make, the more our profit. Our profit's going to be $30 per radio, right? 90 minus 60. So our profit will be that, I'm gonna consider 100 one of my endpoints actually, right? Because 0 radios, obviously we're not gonna make anything. So 100, I'm gonna call that an endpoint, and we're gonna make 30 for every radio, so 30 times 100 is 3,000, right? So we're gonna make $3,000 if we do 100. Now what's our profit after that? So I'm only really concerned with greater than or equal to 100, right? Okay, so that's one way to do it. Okay, another way to do it though, now obviously some of you had some difficulty with that, I can tell by the looks on your faces, right? Thinking your way through that. So here's another way to do it. Think of it as an ordered pair. Anytime you get a problem, it says for every time this one changes, this is going to change by this much. That's a linear relationship. So let's just make an ordered pair. Here's X, here's P. Let's make a little table, an XY table. X is the units, P is the price. So for 100 radios, what's my price? 90. For 101 radios, what's my price? 89.90. There you go. What do you need to write an equation of a line? You need a point and a slope, right? You need a point and a slope. Well, there we got 2 points. Can we get a slope from that? Right? We subtract the y's. So on top, let's go 90 minus 89.90. On the bottom, we'll go 100 minus 101. This would be price. So this is dollars. This is units. So this would be price per unit, right? This would be price per unit right here. So this would be my equation. So P equals, or Y equals, but we'll use P here. The slope, so what do we get here? We get 0.10 over negative 1. So that's negative 0.10. So I got my slope. This is just like doing a tangent line, right? This is just like doing a tangent line. So I got my slope. I got X minus my X point. Let's pick this point right here. X minus 100 plus my Y value, 90. Now look at that equation. Look at that equation. They're the same, right? Now then, is that easier? To me, that seems pretty easy, right? If I know for 100 radios, I'm going to have a price of 90. For 101 radios, I'm going to have a price of 89.90. Then let's just write that down as 2 points. Let's do a slope. Let's do our point slope form of our line, and then we got our price equation. Now we can go ahead and sit. Now that's this right here that we're finding, right? So that's P equals negative 0.10 X, and then we distribute there. We get plus 10, plus 90. So that's P equals negative 0.10 X plus 100. So now my profit is going to be X times that. Well, I can do that in my head. So I'm going to take X times that. So that's going to be negative 0.10 X squared plus 100X minus, what's my cost? 60X, right? $60 for every radio. So my big P equation ends up being negative 0.10 X squared plus 40X. That's what I'm trying to maximize, right? So I do P primed. I get negative 0.20 X plus 40. Where does that equal 0? That is when X equals 200, okay? Now, I think you can do a list of candidates here where you could go P of 100. We said 100 radios is when we start charging less. So 100, you plug 100 into your profit equation, you're going to get 3,000. You plug 200 into your profit equation, you're going to get 4,000. So that's more, okay? And then it's going to drop off from there. And then, like Sam was saying this morning, that's an upside down parabola, so it's going to go down, 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 and when you start charging less. So you could do list of candidates. You could do a number line at 200. You can do a number line and just show it's increasing and decreasing. Talk about that. Okay, so you got to do that justification, okay, somehow. But the answer was how many radios, right? So 200 radio order would be the best. Otherwise, you're going to be dropping the price too much, right? So what the manufacturer would do is say, okay, we're going to be $90 a radio, but if you want to order more than 100, we'll knock off 10 cents for every one up to 200. They would say up to 200. Then after 200, they probably keep the price consistent, you know, and whatever. Okay. So that's 19. So now look at 20. So 20 is the same exact thing. 20 is the same exact thing with the apartments. Okay, we won't go through the whole thing, but basically, if you want to set, one way to set it up is what's the price of the apartments? $540. Now remember that you're the apartment owner, so your revenue is the rent, right? That's your profit, or not your profit, that's your revenue. That's the money you're getting as a rent. And then the cost is what it costs you to clean the apartments and the electricity and all that stuff. And that's the $36 per unit. But only the ones that are occupied, right? So you can just let X be the occupied units, probably is the way to do it. I don't know if this is how I did it on the answer sheet. Sometimes I do it with the unoccupied units, doesn't matter. So if X is the occupied unit. So one way to do it is just say, okay, I got 540 is my rent, but I'm going to add $30 for every what? The rent goes up $30 for every empty one, isn't it? For every unoccupied apartment, right? For every unoccupied apartment. Well, what would be the unoccupied apartment? If X is occupied, 50 minus X.
It says for
Vacant.
for each $30 increase in the rent, however, an average of 1 unit.
Right, yeah, it's not like you're gonna raise the price, but that's basically what it's saying is, if that's what'll happen first, if you raise the price, it'll be harder to get people to come, right? That's what they're saying, right? You lower the price, people say, hey, that's a great deal, those are good apartments, I'm gonna get it, right? But somebody will say, hey, it's too expensive, so what they're saying is, it seems like, this is through market research or whatever, every time we raise it 30, it's essentially one less apartment's going to be occupied. But so that's basically what we're saying. Okay, so it's going to be 540, but the price is up 30 every time there's an unoccupied apartment. It doesn't matter which happens first. But that's 50 minus X. Okay, so one way is just think your way through it. So this is going to be the rent, or we'll call that little p, the price. That's our revenue. That's the money we're getting in on each apartment. Okay, so one way is just think your way through it. The other way is to say, okay, if X is a number of units, so if I have 50 units, my price, my rent is 540. If I have 49 units, my rent is 570. You see what I'm saying? So you can just set it up as an order pen. Okay, now do a slope calculation. So 540 minus 570, 50 minus 49, we get negative 30 over 1. So we get negative 30. So your equation would be negative 30, X minus, pick this point right here, 50 plus 540. Now, are those two the same? Well, they kind of look different until you actually work them out. This would be plus 1500 plus 540. This would be negative 30X plus what, 2040? Did I do that right? This one would be 1500 minus 30X. And then you look at that and you say, oh yeah, 2040 minus 30X is going to be the same thing. Right? So this is a pretty easy way to come up. So when you get into these story problems, and they're going to be easy to identify. They're a business kind of a story problem. They have to do with profit. And you see that every time this one goes up, this one goes down a certain amount. That's a linear relationship. Write down a couple of ordered pairs, get a slope, write an equation. That's your price equation. Okay? So that's basically how you get a price equation for one of these scenarios. Okay, then all you have to do is take X, just like we did here, you just take X times that, so you're going to take X times this, that's going to be your revenue, minus the, what was it, 36X on this one, $36 per apartment, so 36 times X, minus, that is your cost, you subtract those, you do the derivative weight, you got the answers. Okay, let's stop there, and that's kind of some of the business, kind of the max profit kind of situation. So what I want to do next is, so right here in this short amount of time, we're going to be touching on a little bit of everything that is on the quiz. We did a little bit of related rates there. We did a little bit of max min. And now we're going to go back and revisit parametric for a little while. So we're going to work on this for a while in class. And then then I'll give you your assignment. And your assignment's going to be more packet and optimization kinds of stuff here. Okay. All right. So let's talk about Luke Skywalker a little bit. All right. Go ahead and read it first. Okay, so graph that in your graphing calculators. Graph that, give yourself a reasonable window, set your T range, that kind of stuff, and then we'll draw a little picture of this on our paper here. Because the y goes from -2 to 2, right? And the x is going to go from -1 to 1, right? So if we're going to look at this situation, so let's graph that. Let's graph that on our paper here. So if we've got, I'm going to go off to the side here and just graph this scenario. Leave myself some room. So we're up here. And then did you just leave the t alone, -0 to 2 pi? Probably did it, right? The 0 to 6.28, isn't that the default setting for the t range? And that'd be good, right? Because that'd give you one rotation around. So.
Mine's not that.
Yeah. So
It's what?
it's like the.
Okay, but now think about this. What kind of window did you set? Yeah, see, think about your window. You can make it look any way you want depending on how you set your window. Now, your window, your screen, look at your screen. Is your screen taller or is it wider? The screen is wider in a rectangular way, right? So to make things on your graph look realistic, the way they're supposed to, you need to set an X window that is bigger than on the X than is on the Y. And it's roughly, it's not twice as big, it's about 1.5 as big. So I think a good window to set here would be, let's do a -6 to 6 on the X and a -4 to 4 on the Y. You want about a 3 to 2 ratio of your X and Y window to get a good picture. Is that better?
Yeah.
Usually it doesn't matter. We don't care about the realism of the graph, you know. But like if you graph a line y equals x, it should be a 45-degree line. It should be 45 degrees, right? But if you change your window, you can make that thing look steep or look shallow. I mean, just depending on the size of your window, right? Should be 45 degrees, but only if you do a square window. Now there is a setting in your window zoom. There's something called zoom square, but that doesn't always make the window big enough for you to see it. Okay, now tell me what's going on here with Luke. First of all, what direction of travel do we have around this thing? One of the things you have to do is mark direction of travel on a parametric graph. Do you know how to do that right now on your calculator to see which way? Trace, right? Trace. Now, I think you are correct, Max. I think you're going to see that it's counterclockwise. Right? So he's caught in this tractor beam, right? Circling the origin, right? Circling this planet. And he needs to get to the rebel base. And the rebel base is where? What?
My trace isn't like so
how come your trace doesn't work? I don't know. Well, yeah. I may just give you a different calculator for the quiz when we get to that point. Okay. Is that what your question was basically? How, if I have to do that on the quiz, how am I going to do it, right? All right. So when you hit the right arrow, what happens? Does he move?
It like jumped through the spot.
I don't know. That's weird. All right. So where does he want to go? So that's down here, right? He wants to get down here at 0, -4. So what's he going to have to do? Well, it tells you what he's going to do. He's going to have to, he can use the force to shut down the tractor beam, but it's going to wipe out his ship's power, right? So at the minute he wipes out the tractor beam, his ship will just start floating. Whatever speed he was going, he'll just continue going at that speed, right? It's kind of like you're swinging something around, right, like this, and you let it go, right? It's just going to, whatever direction it was heading, it's just going to take off, it's going to keep going. But we're out in space, so he's going to maintain that speed the rest of the time, right? So where do you think he's going to have to shut this down at? It's going to be at some point, so basically we're talking about a tangent line on this, right? And where do you think it'll be about?
Kind of midway through almost 1
In the third quadrant? Somewhere over here? Right? So let's draw that in. Let's draw a tangent line. So something like that, right? Like somewhere right around here. Right? Do we know the coordinates of that point? What can we call them? X, Y. See how this is Shanghai now? Shanghai problem was when you had a tangent line, but you didn't know where it was touching the curve. Right? So what we need to do is find that point. Now we have up above here, I can't scroll up, but we know what X and Y are. X is equal to cosine t, and Y is equal to 2 sine t, right? So we have things, we know what X and Y are that we can use. Okay, so I could substitute those in right here at any time, right? I can substitute them in now or later or whatever. Now what was the key to Shanghai? What was the key to Shanghai? Come on, it wasn't that long ago. It was only a couple of days ago. 2 different ways of doing the slope. 2 different ways of doing the slope. One is, well, slope between 2 points. Well, do you have 2 points here? Yes. And the other was derivative. Now, in this case, it's parametric, though. How do we do slope of a parametric graph? I just had it up in the notes earlier, y prime over x prime, right? So we can do y prime over x prime is the slope, but also we can do the slope between these 2 points. Those have to be equal to each other. There you go. I've given you just everything you need to do, right? So now that's how you're going to find what this point is. If you know what that point is, now you can do the speed. Do we have a way of figuring out how fast he's going around that path? Do we have a formula for speed of parametric? Sure we do, with the square root, right? We've got a formula for speed. We can figure out how fast he's going. If we know how fast he's going, we can figure out how far this is. We can figure out how long it's going to take him to get there. So is he going to get there in time? Blah, 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 blah. It says 3 minutes. Okay, you got all the tools you need. You got all the tools you need. So let's work on this for a while. And you can help each other out and ask each other if you want.
Wait, you said the derivative to the slope of the 2 points?
You have 2 ways of doing slope of that line. You have 2 ways of doing slope of that line. It's the same line, so they have to be equal to each other, right? One way is the slope between 2 points. You got 2 points right there. One way is to do a slope calculation. The other way is to do the slope of a parametric path, which was on the very first slide I showed today. It's in your notes. Go back to your parametric notes. Go back to your parametric notes. What's the slope of a parametric path? Right. That's what this is. That's the slope. This is a parametric graph. That's a slope of it right there. Is that equation right there? But also the slope between those 2 points is also the slope of it. So you set both of those up, set them equal to each other.
The t primes cancel.
There won't be any t primes. Why do you have a t prime? You're doing the derivative with respect to t. When you do the derivative of x, You talking about doing the
Yeah.
x prime and y prime?
So
There's no t prime. You're doing the derivative with respect to t.
so it's not the derivative of cosine.
It is.
It's just like cosine x.
Yeah, it's, if you have x of t equals cosine t, then x prime of t is negative sine t. You're just doing the derivative of x with respect to t.
Okay.
So t prime would just be dt over dt. It's just one. Yeah, there is no t prime. There is no t prime. Just like in a normal cosine x equation, there is no x prime. Just set it up, Emily. Just write the equation. How do you do the equation? How do you do the slope of 2 points?
I get the minus one.
There you go. Yeah, start writing that down. Yeah.
I get that.
Okay, and you know what y is up above in your equation. You know what y is, so put that instead. Instead of y, put that. What's y? And you can just use your calculator to solve. Right? And your t is between, well, what's your t going to be between? Don't you know about where t is? Between what? We know it's in the third quadrant. Remember what t is? T is your theta basically around, right? So it's somewhere between pi and 3 pi halves, right? So you can do a vertical bar and you can solve. You know it's going to be in between there somewhere. Right, but that's what I'm just saying. But you know what y is? Y is that? So put that in. Right. And then you know what x is at, so put that in place of that. And you got an equation with just t in it, and just put that in after and solve. That whole big mess, just solve. But again, this is, I want to reemphasize, this is Shanghai, this is Luke Skywalker. Later, the rest of this year, we're going to either call it Shanghai or Luke Skywalker or whatever. Two different ways to do slope. You've got a tangent line where you don't know where it's touching the curve, but you should know some other point, which like we do here, you do two different ways to do slope. One is slope between 2 points. The other is your derivative. In this case, it's parametric derivative, which is slope of the path, which is y prime over x prime.
Okay, so after you like put in your x prime and your y prime over x prime and then the slope.
You solve it. You should just have a big equation, like a big fraction. You should have something over something equals something over something. Right? Just solve that big equation. Yeah, you don't need to mess with cross multiplying or anything.
But
That's
it's
great.
like a biggie.
Huh?
I just don't know what
You did what?
That's what I was trying to work out.
That's fine. I don't mind doing that. That seems reasonable. It's got to be more than pi, right? Did it come out like that?
Not like that.
Oh, good. I was thinking, let's say 7 pi 6. 6. What's 7 pi over 6? Yeah, but maybe it isn't. Maybe it isn't. Maybe it might be everybody's fault. Well, I just wondered when you did all that math, all that stuff in your head, or not, because you wrote that all out, you just.
Why does it say like into in my?
What?
It says like into in my answer.
Yeah, I think it is 7 by 6.
It is.
Well, that's because you didn't limit it. That's why we said, Will, we said you only care about between pi and 3 pi half.
Oh,
So if you do the vertical bar, then it won't give you all those. So what did you do? Where'd you get that? That's okay. Go ahead and write it down. Getting 7 by 6?
Where was it?
Because outside of
oh, it does.
So, yeah. It's
okay, that was why. Okay, that's one way, that's the slope of that. Because you just do slope. Another way you do slope of half was the slope of half. So that's why.
That's times,
These are both ways to do the slope of this line, right? One is this equation, slope of that. One is just our.
Yeah.
There you go. Now you're just solving that, and your T is your theta, right? So you just do slope.
So is this a?
Here's, you did 500, 72. So you can go up, I got it.
I'll see what's right.
That's what I'm saying. If you go to your- Sure, this is 1/2. If you divide that with 1/2, where's sine on there? 8 by 6.
Is this a calculator problem?
For sure.
Okay. So we can use.
For sure.
So when you like the points, you just plug in trace T at 7
So-
by 6.
So 7 pi 6 or 3.66 whatever light years, whatever time units we're using here. Okay? And so now that is the time, that is the T value. So, and we can plug that back in to get the X and Y coordinates, but I don't know that we need the X and Y coordinates to answer any of the questions. The question is, when should he shut down the tractor beam? 7 by 6, right? That's a time. Find the equation for the path he will follow after that time. What? You just need a point and a slope. So you do need the point for that, right? So that'd just be your y equals m times, right? So to get the slope, well, you got two different ones for slope there, right? You got the two things you said equally good. So you can either do your y prime over x prime, or you can do your other one, right? Both of those are the slope of that line. So just plug 7 pi 6 into one of those fractions. Why are you looking at me like I'm crazy?
that's your slope.
So you,
That's a slope of your line,
so
right?
you like, if you plug it in and so it gives me negative 0.866 and then comma negative 1, I could use that for the slope too.
Yeah.
Okay.
Say that again. Can you use what for the slope?
I plugged in T at 3.66519.
Oh yeah, you could just trace to 7 pi 6 and get that point. Right, yeah, you just trace there, that's your point. And then your slope, you would need to calculate from what you already had written down. Right, you can use decimals. If you use three decimal places, it's fine.
Then we can use the 0, negative 0. No, it's 0. After we find the slope,
What's that?
we can use the 0, negative 4 to look at this.
Yeah, well, right here, Emily. So right here, remember, this side was the slope of that line. And this side was the slope of that line, right?
So I put 7 pi 6 and then on the line.
There you go. That's it. That's the slope. Yeah. So you put 7 pi 6 into this one, and that's the slope. Now, if you put 7 pi 6 over here, you should get the same thing, right? Now, I got this as the point where they cross right here. Or I mean, that's this point where, not where they cross, where that's a 3, root 3. Negative root 3 over 2, or 0.866, whatever. I mean, I don't care, you can decimal or whatever. So that's the point where he actually goes, right? So you're going to have y equals, and then your slope.
So you have to use that. You can't use the 0.
No, you can use 0 for it. Because it's all in line.
Yeah, you can use the negative 4. Yeah, oh yeah, that'd be the easier one. What'd you get for the slope? Negative 2.
I got negative.
Yeah.
I think negative 3.4 or something. Yeah. I think that's same as 2 root 3. Negative 2 root 3. So yeah, and 0, negative 4, well, that's your y-intercept. So that's easy. That's actually even easier. So negative 2 root 3 x minus 4, that'd be your line. Right? Yeah, using the y-intercept would be smart instead of using that other point. And then, okay, so then what's the rest of it? So that's the equation for the path to follow. Exerting this level of power is extremely fatiguing, and Luke can only keep it up for 3 minutes. Will he be able to keep the tractor beam shut down until he reaches the rebel base? So what do we need to know?
How long is it?
Well, we need to know how long it's going to take him, right? I mean, is it going to take him 3 minutes, right? I mean, that's what it says. But I mean, what do we need to know to be able to answer that?
How far it is.
We need to know how far it is from this point to this point. How do you do that?
Square root.
Distance formula. There you go. Go. Do it. Let's find out how far that is. We got to find out how far that is. Okay? So that's just distance formula between 2 points. Right? The calculus is over now. Well, not really. Not really, because we still got one other thing we got to do here.
You subtract the x's and y.
You subtract the x's and then square it, subtract the y's and then square it. What'd you get?
Route 39 over 2.
That's what I get.
Root 39 over 2. It's just these 2 points. It's just these 2 points. Oh, I'm frozen. Just these 2 points in red here, right? It's just this point and this point. Just the distance between those. So root 39 over 2, 3.122, whatever, distance unit we're using here. Okay? So what else do we need? That's the distance. That's how far apart they are.
Speed.
We need to, how fast he's going. How do we get that? The speed equation for parametric path, right? Because that's what his speed on that path at that instant when he shuts it all down, however fast he was going right there, that's how fast he's going to go the rest of the time, right? So you're swinging something around, you let her go, boom, wherever fast it was going at that instant. So we need that speed equation. That was square root of x prime squared plus y prime squared. So we got our x prime and y prime already, right? Or they're easy to get. And then we got to plug in a what to them? We got to plug in a t-value. What t-value? We'll plug in that 7 pi 6 because that's the time when they were there. So we got to take our x prime, take our y prime, plug 7 pi 6, and then plug them into that speed formula. That's right. What do you get for that? Anybody got it? Root 13 over 2. What is that as a decimal? 803. What's that? Well, what's x prime? Negative sign, right? X prime is negative sine t.
Oh, yeah, I was looking at it on
I got root 5.
Well, here's x prime right here. X prime's right down here. Exactly. Right.
Yeah.
So you just need negative sine t, put a 7 pi 6. So negative sine of 7 pi 6. And what's y prime? Y prime is 2 cosine. So I don't know what do you mean by you put them together?
Well, like, I was just looking at this, the 2 cosine t over negative sine t, and then I forgot that that was y prime. That's
You put 7 pi 6 in that and divided them? You mean?
well, I didn't, because I knew that wasn't right.
Yeah, no, just y prime. You just, yeah. Well, you know, you're right. This is y prime, right? So you just take y prime, put in 7 pi 6, and then square it. Okay. So square root of 13 over 2, and then what do you do with those numbers? Distance equals rate times time, right? So you take distance divided by the rate. So you're going to take 3.122 divided by 1.803, or whatever, square root of 39 over 2 divided by square root of 13 over 2. And what do you get? Root 3, which is 1.732. So he makes it, right? Easily. Cool. Good. He's gonna live. That's a good problem. That does a lot of stuff, right? We got to use our slope on our path. We got our speed limit, or speed law. We got our speed law. We got our speed equation. We got a Shanghai situation. We got an unknown tangent line. Unknown point where it touches. So we can do a slope between 2 points or the slope of the path. We can do that, and so we got to use a bunch of different things from our parametric.
Maybe I typed it because I got root 5 over 2.
Your negative is outside of the square, it looks like on that first one.
Why?
See what I mean?
Yeah.
If you're gonna be squaring stuff,
I
well,
don't
yeah,
even know what
just
that-
keep the negative in. What's that?
Why is your cloth on
Because I'm frozen. Or I mean, because I'm on the green border here. Whenever I go into this annotate mode where I write over top, it freezes the screen, and so I'm writing over top of kind of the frozen screen.
it? Is that?
That's why I can't scroll. What's that?
Is that what?
Well, this thing, yeah, sort of, kind of. The reason I had to connect this is that I defined this is like a smartboard thing, I defined my space to be bigger, so when I get that blank white paper, I don't get that little square, I get the bigger one. That's the only reason I do that. No, what this actually is, it's kind of cool. What's that? Yeah, it's basically a smartboard, but the tablet is the same, does the same thing. I just like the tablet because I can move around. But if I would take this, put it about here. Look at this. Oops. I don't think my pen is charged. But I can do this and then I can just write it. I can be writing on here. So all that stuff I do with the tablet, yeah, I can be writing and doing it here, but I don't like that because that hides it. And I'm better with the tablet. So that's what that is. So it just kind of makes your board in the smartboard. But that's kind of weird. I don't know why that tablet's not, why that thing's not working. Okay, so for tomorrow, so we're going to have, so in the business packet, let's do number 21. I think this is exactly what's on your assignment sheet, actually. Business packet 21 and 23. And then in section 4.5, which is back to those related rates, I think there's going to be a cone problem or two. 12, 16, 23, and 26. Okay? What's that?
Wasn't it 840?
Well, that's what we were just talking about. Because I have it frozen. Once I start writing over top of like a worksheet or something, when you get that little green border down there, it's frozen. I'm going to go ahead and give you this, just in case you don't know your plans or whatever. This is what I would normally be handing out tomorrow. This is called the Anton packet. And I call it that because that's the name of the author of the book I got this from. But we won't be doing anything. If you're going to be here tomorrow, then you don't have to worry about it. But in the Anton packet, the first page, front and back, is those related rate kind of problems. Okay, and then the last couple pages are optimization, max-min problems. And so tomorrow we will have some work time on the circled ones. Okay, and then I'll also have up on the website the answers at some point here along the way. And so we'll be working on the circled ones for Monday, all the circled ones, reviewing those things. And
I might have another parametric problem when I sign, so you just have to see the video, probably, it depends what we get to. Okay, so that's what's gonna be happening tomorrow.
It bothers me that that pin's not charged.